Here we're going to use a pretty interesting integral as an excuse to look at one of the more famous sum to product identities there is out there. And sum to product identities are studied by lots of different mathematicians throughout history, but Ramanujan is fairly famous for studying them. That being said, we're going to look at something called the Jacobi triple product. And so that says that the product as m goes from 1 to infinity of, well, this triple, 1 minus x to the 2m, times 1 plus x to the 2m minus 1 times y squared, times 1 plus x to the 2m minus 1 times y to the negative 2 is equal to the sum as n goes over all integers of x to the n squared times y to the 2n. And, well, we're going to prove this, or mostly prove it, and then use it as a tool to calculate the integral which I have at the top of the board. Okay, so let's sketch the proof of this Jacobi triple product. So here's what we'll do. We're going to set f of xy, so this is a function of two variables, equal to the left-hand side of this equation. And so that's our triple product. So the product side of our product to sum identity. And now let's do the following calculation. Let's look at f of x comma xy. So in other words, we're replacing all of the y's, well, with x times y. So let's write out this product. So we have the product as m goes from 1 to infinity. We have 1 minus x to the 2m. And then here we'll have 1 plus x to the 2m plus 1 times y squared. And that's because we pick up an extra x squared, which boosts that x to the 2m minus 1 to an x to the 2m plus 1. And then that's going to be multiplied by 1 plus x to the 2m minus 3 times y to the minus 2. And that's because that picks up an x to the minus 2, which is going to boost that down. But next up, I'm going to factor a couple of things out of this. So notice that now this term is starting lower than it was over here. Here we were starting at an x, let's see, to the first power. And now we're starting at x to the minus first power. That's our m equals 1 term. So if I factor something out, it'll look like 1 plus x to the minus 1 times y to the minus 2. So that's factoring out the extra term from the third part of this triple product. But notice that this middle term is starting at x cubed. So that means it's missing something. It's missing an x to the first power. So if we multiply that back in, we've got to divide by that as well, leaving us with a 1 plus x times y squared. But after doing that, we've shifted this product back to its original form. But its original form we set equal to f of x comma y. Okay, nice. But now what I'm going to do from here is perhaps factor out an x to the minus 1, y to the minus 2 from this numerator. So let's see what that leaves us with. So I'm just going to maybe write that over here real quick. X to the minus 1, y to the minus 2, f of xy. And then my denominator is the same. We have 1 plus xy squared. Then factoring an x to the minus 1, y to the minus 2 out of the second term will simply give us 1. Factoring out of the first term will give us xy squared. Oh, but notice that we get some nice simplification here. In fact, this simplifies simply to the number 1. But let's see what we have. We have f of x comma xy is equal to, now it's going to be x to the minus 1, y to the minus 2 times f of xy. Now, before we move on to the next step, I'm going to expand my original function f of xy as a power series in y. So that's going to be the sum over all integers. So this is really like a Laurent series, if you will, of a sub n of x times y to the 2n. So if we're expanding it as a Laurent series in y, that means the coefficients themselves are functions in x. So that's what we're seeing here. You might say, well, how do we know that we're only going to get even powers of y? Well, notice in our product over here, we only see y with an even power. So that's how we know that. Okay, so now let's take this orange underline and rewrite it into maybe a new functional equation. And that'll be something like this. We have f of xy is equal to x times y squared times f of x comma xy. But now what I'll do is I'll take that equation and I'll expand both sides as these series. So let's start with this left-hand side. So I'll have my sum over all integers of, let's see, we'll have an of x. And then next we'll have, let's see, an x to the 2n plus 1, because here we're replacing all of the y's with x times y. So that's going to pick up an x to the 2n. My extra x here will boost that up. And then I'll have y to the 2n plus 2 because I've got a y squared to boost that up. But now that's going to be equal to the sum over all integers of an of x and then y to the 2n. Okay, great. But next up what I want to do is re-index this sum on the left so that the indices match with the sum on the right. So I'll take all of the n's and I'll replace them with n minus 1. But since I'm summing over all integers, I'm still summing over all integers. So that's going to give me an minus 1 of x, and then I have x to the 2n minus 1, y to the 2n. But now reading this off, we see that a sub n of x is equal to x to the 2n minus 1 times an minus 1 of x. We've got this nice recursion on our a functions. Now let's take that and see where it goes. So let's recall we set our function f of xy equal to the left-hand side, the product side, and then we expanded it as this Laurent series in y, where the coefficients are functions of x. Then we got this nice recursion, or this recursion functional equation on those functions of x. Now we're going to expand these down to get maybe really finish it off, if you will. So for the moment, I'm going to assume that n is bigger than 0. And then technically you would need to repeat this for the case when n is less than 0, but I'll leave that to you. So if n is bigger than 0, we can take this down one step at a time. So the first step will pick up an x to the 2n minus 1, and then the second step will pick up an x to the 2n minus 3, and then an x to the 2n minus 5, all the way down x to the 5th times x cubed times x to the 1st times a 0 of x. So that's simply repeated applications of what we have right there. But check it out. Putting all this together, we have x to the 1 plus 3 plus 5 ending at 2n minus 1 times a naught of x. But it's well known that the sum of the first n odd numbers is the nth square. So that exponent becomes x to the n squared, or I should say the exponent becomes n squared. So we have x to the n squared times a naught of x. And then a similar strategy will work for n less than 0, and you get the same thing. Which means we really just need to know what's happening for the n equals 0 case. In other words, what is a naught of x? And I'm actually going to cheat on this. And that's because it's a little bit tricky. But I'm going to post a video fairly soon where we'll actually see this. That video is about something else, but we will go through a full proof that will get to the point where this a naught is equal to 1. But like I just kind of gave away, this a naught is equal to 1. But if a naught is equal to 1, then an of x is equal to x to the n squared. But if we make that replacement up here, we have the sum over all integers of x to the n squared y to the 2n as needed. Okay, so now let's apply that to our problem. So now to our goal, which is the integral from 0 to infinity of e to the minus x times the product as m goes from 1 to infinity of 1 minus e to the minus 24m times x. Okay, so we're going to start here with a substitution. And that substitution will be to set q equal to e to the minus x. So like I said, we're going to say q is equal to e to the minus x. But what does that mean? Well, so that means that dq is equal to minus e to the minus x. When x is equal to 0, that tells us that q is equal to 1. As x approaches infinity, that has q approaching 0 from above. So those are all of the things we know to make our change of variables. So in the end, this is going to turn into the integral from 0 to 1. You might say, well, shouldn't it be the integral from 1 to 0? But I'm going to take this minus sign right here and have that switch the order of integration. And now we'll have the product as m goes from 1 up to infinity of 1 minus q to the 24m. Okay, and then we'll have dq. Okay, so that is that. So I'm going to take this product and write it as a product of 3 things at a time. So that's going to leave me with the integral from 0 to 1, and then the product as m goes from 1 to infinity of 1 minus q to the 72m, and then 1 minus q to the 72m plus 24, and then 1 minus q to the 72m plus 48, dq. Okay, great. So let's notice that that's capturing everything, but just 3 at a time instead of 1 at a time. And that's simply because 72 divided by 3 is 24. But now this is in the format that we could apply our Jacobi triple product identity. We just have to choose a nice substitution for x and y. And that's the trick here. And this is actually related to a special case of the Jacobi triple product identity known as Euler's pentagonal number theorem. That being said, we're not really going to worry about that at the moment. We're just going to stick with this. So what we want to do is set x equal to q to the 36, and then y squared equal to negative q to the 12. And I just realized that these should be minus signs here instead of plus signs. If we have plus signs, we don't have the correct starting point. Okay, so now under this substitution, well, we can directly apply the Jacobi triple product identity that we have over here. So that's going to leave us with the following. We'll have the integral from 0 to infinity, and now the sum over all integers of, let's see, it'll turn into minus 1 to the m. That's from the fact that we're setting y squared equal to negative q to the 12. That picks up a minus sign. And then we'll have q to the 36m squared plus 12m. That's from combining these two parts right here. Okay, nice. But now I'm going to switch the order of summation and integration. So I have the sum over all integers, minus 1 to the m, and then the integral from 0 to 1 of my q to the 36m squared plus 12m dq. But that's a fairly simple integral. That gives me the sum as m goes over all integers of minus 1 to the m over 36m squared plus 12m plus 1. Oh, and I just realized I've kind of been sloppy with my index. So let's change all of these m's to n's just to make it match what we've had. Okay, there we have it. And then I can factor this, so I've got the sum over all integers n, and then minus 1 to the n over 6n minus 1 squared. Okay, so now let's talk about how to evaluate that sum. So we just collapsed this nice integral into this sum over all integers. And so you can actually have a 6n minus 1 or plus 1 here just because of how this thing is symmetric. So I'll choose the minus 1. So we've got the sum over all integers of minus 1 to the n over 6n minus 1 squared. Now, in a previous video, I proved that the sum as n goes over all integers of f of n is equal to minus the sum of the residue, so now we're using some complex analysis, of the function pi cotangent pi z times f of z at the poles of f of z. And there's a very similar result. It's proved almost exactly the same way, that the alternating sum, so the sum over all integers of minus 1 to the n f of n, is equal to negative the sum of the residues of pi cosecant pi z times f of z at the poles of f of z. Notice that the function we would take would be 1 over 6z minus 1 quantity squared, which has a double pole at 1 over 6. So that's what we'll use. So this is going to be equal to minus pi times the residue at z equals 1 over 6 of the cosecant of pi z over 6z minus 1 squared. But now we need to use the formula to calculate this. The formula for calculating a residue at a second order pole, which involves multiplying by, well, we're going to multiply by z minus 1 over 6 squared and then taking the derivative. So let's do that. So we're going to have minus pi and then the limit as z goes to 1/6 of the derivative with respect to z of z minus 1 over 6 squared over 6z minus 1 squared times cosecant of pi z. Okay, great. So that's multiplying by z minus the pole, squared in this case, and then taking the derivative. And then that minus pi, well, it comes from the pi here and then the minus sign. Okay, but let's notice that this simplifies fairly handily. And what does it simplify to? Well, all of that is going to simplify to 1 over 36. So that's going to leave us with minus pi over 36. And then we have the limit as z goes to 1/6. Now let's take the derivative of cosecant, which is minus cotangent times cosecant. But another pi is going to pop out because we have a pi here. I'll put that as a pi squared here. Then, like I said, we're going to have cotangent pi z and then cosecant pi z. And another minus sign is going to pop out. Like I said, I'll have that cancel the minus sign that's out front. But now both of those are continuous at 1 over 6, so we can simply plug it in. That's going to leave us with pi over 36. And then by the definition of cotangent and cosecant, we'll have cos pi over 6 over sine squared pi over 6. But those are well-known values of those two trig functions, so we can put everything together and we'll end up with pi squared times the square root of 3 over 18 as our final answer. And that's a good place to stop.
Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.